All right, everyone. So we are going to go over topic 5 today, which is bending. So you should all be able to find the link to this PowerPoint PDF online so you can follow along. And the objectives of today's lecture are going to be to determine the stress in beams caused by bending and to look into internal shear and moment of beams. So this part here is really just a review on shear and moment diagrams, okay? And so this is kind of from statics. This isn't really new. We'll have a little statics review. And then we're going to actually, this is kind of out of order, we're going to then take this to determine the stress in beams caused by bending and calculate bending stress, okay? So the first thing we're going to do is let's talk about what a beam is, right? So I'm sure you guys have heard this term in statics, and you've heard me say it a lot, and your other professors probably have said it a lot too. So it's a good time to make sure we understand exactly what a beam is. Okay, so a beam is basically just a long, slender member that supports loads perpendicular to the longitudinal axis. So what that means is if this is the longitudinal axis of my beam, any load in this direction perpendicular to it, this is what beams typically are loaded. Okay, some examples of beams or some other words we sometimes use to describe beams. We have joists. Okay, you might also see girders. Those are like large beams. Joists are like small beams. And then you could even say that a bridge, is an example of just a really big beam. Right? Because we have a bridge and then it's supporting some load, right? Some point loads, some distributed load. So really this bridge can be looked at as just like a really big beam, okay? So they're super important structures and we often classify them based on the type of supports that they have. So you might have heard this word simply, or this term simply, supported beam. That just means that we have a pin and a roller system here. Cantilever beam means it's just supported at one end with a fixed support, and then we have a free end here. And then an overhanging beam means this support's kind of pushed in a little bit. It's not quite at the end like a simply supported beam, okay? So why are beams important? Why do we need to study them? Well, beams are one of the most important structural members because we find them in almost every single structural model or building or, different types of structures that we design. So for example, like I said, a bridge can be looked at as a really big beam. And then another a common type of structure, right, are buildings, and buildings are full of beams. So they're used to support the floor of a building, the deck of a building. The wing of an aircraft is another example of a beam. So that's not so much civil engineering. That would be more mechanical or aerospace engineering right there. But we see a lot of real world examples of beams. And if you do go into structural engineering, you'll need to be very good at identifying what a beam is, okay? So what happens internally when we apply loads on the beam? So if we kind of think about statics, right, we were interested in statics. If this is our beam and we have some type of loading, we want to find the reactions that this loading causes. We might want to make a cut and find V and M and even N, the normal force, our shear force, our moment that's happening at some cut. This is all kind of static stuff, right? Now when we get to materials, what we want to know is that, okay, we get that some load P is applied to the beam, but when that load is applied, what happens internally? What's happening inside of that member? And that's really dependent on the type of material that you're using, right? So we're going to start talking about how that load is transferred to stress inside of a beam. Okay, and this is similar to our torque discussion, how we kind of derived that formula for relating our torque, our torque T to our shear stress tau, right? So we're going to do the same thing and relate M, that applied moment, to our normal stress sigma. Okay, but before we can get to that point, we need to make sure that we're really good at figuring out how to get this internal moment. Because just like we related internal torque and tau, we need to figure out how to get the internal torque. We made all these cuts to get internal torque, and then we were able to plug it into that formula. We need to make sure we're really good at getting this moment. Okay, so this is going to give us a little bit of a statics review here, because how do we find the moment? We make a cut, right? And then we can make a shear and moment diagram, or we can do the equation approach. So we're going to go over the graphical approach and the equation method, and kind of mix it up and do a little bit of both. And I also have a really comprehensive PowerPoint that I posted on Titanium for you that goes into a lot of depth about shear and moment diagrams, and basically has everything that you'll need to know about how to create a shear and moment diagram for a beam. So if you feel like you're a little bit fuzzy in that subject, I strongly suggest that you go online and take, a half hour, an hour, however much you need to kind of go through every single one of those examples, because you'll have to use shear and moment diagrams for a lot of other classes. So it's best to just kind of get comfortable with it now, okay? So let's continue. This is actually also pulled from the book and from that shear moment PowerPoint that I posted online, but this is just to remind us that this is our sign convention that we generally use. So this would be positive shear, this would be positive moment, and actually this is positive distributed load, but we know typically our distributed load looks like this going down, and so that's why this would actually be negative W, okay? So let's do an example. All right, so this is which kind of beam again? We have our support that's pushed in. This is called an overhanging beam. Okay, we have a pin and a roller, and we want to express the internal shear and moment in terms of X, and then draw the shear and moment for the overhanging beam. Okay, so let's see what we can do. All right, let me get this. Okay, so let's draw first these reactions. Okay, and we have this resultant force, right? The 6 times 6, the total length of the beam is 6. 6 times 6, I have 36 kilonewtons right here. Okay, and I want to solve for AY and BY, so I'm going to start by summing moments. Okay, so I'll do that right here. Sum of moments about A equals 0. Counterclockwise is positive. And I have BY times 4 minus 6 times 6. That's the 36 times a moment arm of 3. And I get BY of 27 kilonewtons. Okay, so I'm going to put that down here, 27 kilonewtons. And I'm going to take the sum of forces in the y direction. Up is positive, that's my sign convention. AY plus 27, what we just solved for, the BY, minus 36 equals 0. And I get AY is 9 kilonewtons. Okay. Good. So now we want to find the shear and moment. So V and M in terms of X, which means X is any point along that beam, right? So here, what we first need to figure out is how many cuts do we need to make along this beam in order to get a function of moment, right? So how many cuts? We would actually need 2, right? Because from 0 to 4 meters, we have no change, but then from 4 to 6 meters, we do have a change. We have the roller, right? So we need to make a cut anywhere there's a discontinuity. Okay, so let's start. Let's go with cut number 1. Okay, and here is my beam. Kind of cut it somewhere along that beam, and I've exposed some V, some M. I still have my distributed load. This is, I'm going to call it X1. And so here I would have 6X1. And just to be clear, X1 here is between 0 and 4. Okay. And we can put in, we know AY here is 9 kilonewtons, right? All right. So let's start by summing forces in the y direction. Up is positive. 9 minus 6x minus v is 0. And we can get v of x1 is equal to 9 minus 6x1. We have one function done. Let's do the same thing for a moment. We get that moment that we just made the cut at plus 6x, and it acts x over 2 away, right? This distance here is x over 2, x1 over 2 really, and then minus 9x equals 0. And we can solve, say m of x1 is equal to 9x minus 3x. I'm going to put x1 so we know this is for x1, right? And then an interesting finding here, right? You guys should all remember this. Shear is the derivative of moment, right? So if we take the derivative to check, we get m prime of x1 is 9 minus 6x1. Look at that. That's our shear. Check, we did it right. You could have also taken the integral of this, right? 9x1 minus 3x1 squared. And of course, we'd need that plus c, that plus constant. And all we'd have to do here is recognize that at x equals 0, we don't have a moment applied, so this goes away. Okay, so this is cool. We can use math, we can use statics, and we should always get the same answer. So there are so many checks when you're doing your shear moment diagrams. I don't even really have to post the solutions for you guys to your suggested problems because you guys should be able to check this yourself, right? Okay, so let's do our second cut. Okay, and this is going to be for x between 4 and 6. Okay. And I'm just going to cut from the other direction now. It doesn't matter. You can do whichever direction you want as long as you're just keeping track of your equations. Okay, and I'm going to call this x2, oops, not the slanted line, x2. And now we've exposed some v and some m. And again, I have this 6x2 right here, okay? And I'm going to do the same thing now. I'm going to sum forces in the y direction, set them equal to 0. Up is positive, and I get v is equal to 6x2. Really, this is v of x2, actually. Let me write that down. V of x2, okay? And I can sum moments, set them equal to 0. Counterclockwise is positive. I get negative m minus 6x2 times x2 over 2 is 0. And I can solve for m of x2 as negative 3x2 squared. Okay, so now we have our functions for moment, and we're ready to draw our shear moment diagrams, okay? So I'm going to redraw our beam right here, okay? And I'm going to put our load and our reactions. We have 27 and we have 9, and this here is a 12, right? Because this was 6 originally. Okay, and now let's draw our axes for shear, for moment. Shear is in kilonewtons, moment is in kilonewton meter. Okay. And now, so we kind of did the equation approach first, and you're welcome to kind of graph those equations. But for anything that's simpler than a triangular distributed load, which most of the time those are the kinds of loads we're dealing with, we can kind of just use the graphical approach, which is a lot easier. So let's do the graphical approach. I'm going to start here at x equals 0. I'll put this in a different color so we can see what's happening. I'm starting here at x equals 0, okay? And what shear do I have at x equals 0? I have a shear of 9. Right? That's this, okay? I know because my distributed load, or my beam is loaded with this distributed load of 6 kilonewton per meter, right? It's constant, right? This is a constant distributed load. So I know if W is constant, that means shear has to be a straight line. Has to be a straight line. Okay. Now, that means that, let's come here. Let's come to this point where we know what's happening here, okay? At this point, I'm going from 9. I know I have a straight line, and I know I'm going to have to be basically connecting to some point down here, right? I have to be going down. And then I'm going to have to be pushed up at this point by 27. Let me draw that a little more straight. Okay, why do I know that I have to be going down like that, like this straight line right here? Because W is negative. That means I have a negative slope of this line. Okay, that's why I know that. Then I end up being pushed up by 27. So right here, I get to negative 15 plus 27 puts me at 12. And then this pushes me back to 0. Okay, and all you have to do to get those numbers, if you're not seeing where they're coming from, is from here to here we have 4 meters. From here to here we have 2 meters. So we'd have a 4 times 6, which is 36. 9 minus 36 puts us at negative 27 there, okay? So everything has to add up appropriately, okay? All right, so let's continue. Here, let's draw our lines in. So we know if we have a 0, that means we're going to have either a local min or a local max for our moment, okay? We know we're starting at 0, okay? And we know we're ending at 0. So we have to figure out what happens in between. Since this is a straight line, since V is straight, we know M is a parabola, or a second order function, right? So if we're starting at 0, how do we figure out what this point is here? It's a maximum because we're going from a positive area, which means we're adding from this point, this 0 point. How much do we add? Well, we add 1/2 times 9, and we have to find out what this 0 is, okay? How do we find out what the 0 is? So times base. Well, we go to our function. So let's go to our function from 0 to 4 for shear. And we want to say, when does this equal 0? Well, it equals 0 when x1 is 9 divided by 6, 1.5. So this would be times 1.5. 0.5 times 1.5 times 9, we get 6.75. So we take 0, we add 6.75, and that's what this value is, okay? Now, how do we draw the line, or the curve, the parabola that connects the 0 mark and the 6.75? Well, we look at the slope of that line, right? It's going from increasingly negative to less negative, right? So, I'm sorry, increasingly positive. Sorry, they're positive, right? We have a positive 9, that's going to be our slope here. And we have a 0, that's going to be our slope here. We have to connect it like this, okay? On the other side too, right? 0 slope, most negative slope here. So we have to connect it back. And if you take the area under this portion, it should bring you back to the point that you're looking at, right? That 0. Oh, I'm sorry. Actually, no. It needs to bring you back to, that's why I made a mistake here. Let's take a step back. I actually don't know this point here, right? I don't know what that point's going to be. I'm not sure where on this line, because this isn't symmetrical, right? We have an overhanging beam, so I need to find this area. So the area here is 1/2 times 15 times the length from here to here is going to be 4 minus 1.5, which is 2.5. So times 2.5, so that's 0.5. 2.5 times 15 times 2.5, and I get 18.75. So I need to go 6.75 minus 18.75, and I get negative 12. That's how I get this point. So I took 6.75, and now I know it has to start from 0 slope here, and I get increasingly more negative slope. Why do I know it's a negative slope? Because here it tells me the value is negative 15. Okay, that's how I connect that. And then here, I go again from a negative slope to something flatter out here at 0. Okay, and that's how I know how to draw this diagram. So if this was confusing for you at all and you're having some issues with it, you can either post on the chat some questions for me, or you can go, or actually before you post a question, please go and look at the shear moment diagram PDF that I have for you on titanium, then come and ask me your questions, okay? And if I'll know if you did, because I'm going to ask you questions about it. So hopefully those will clear up all your questions. Okay, so here is an in-class assignment. So at this point, it would be good for you, be beneficial for you to kind of pause this video, okay, and take your time to solve this problem on your own, okay? And this is really what's going to test your ability and see, hey, do I know shear moment diagrams? Am I good with it? Do I need to continue kind of reviewing or not? Okay, so this is like a little test for yourself, and then you can restart this video. So I'll give you guys, you can stop it now, try it, and then restart, and I'm going to put the solution here for you right now, okay? So what's happening here is we want to draw the shear moment diagrams for the beam and determine all equations for shear and moment along the beam as a function of x, okay? So let us start by summing the moments about point A, setting them equal to 0, okay? And we get cy times 10 minus 25 times 7.5. The 25 is just the resultant here. Minus 15 times 5 minus 80. And then we can solve for cy as 34.25 kilonewtons. Okay. And we can sum forces in the y. And we get ay plus 34.25 minus 15 minus 25. And we can solve for ay as 5.75 kilonewtons, okay? Now let's make our first cut, okay? So actually, before we make our first cut, I might have given it away, but how many cuts do we need here? Okay, we start at this point, no change, no change, no change until we get to this point. So it means we need to cut here. And then there's some change, so we need to cut here. So we need 2 cuts. Okay, so cut 1 is going to be from 0 is less than or equal to 5, x is less than or equal to 5. So between 0 and 5. Okay, so let's draw this cut. And I don't have any load actually until this point. So this is x1, and I have here the 80 kilonewton meters, and I already solved for this 5.75 kilonewtons. And of course I made a cut, so I always expose internal shear and moment. Okay, now I'm going to solve for these by summing forces in the y direction, okay, and I get negative v plus 5.75 equals 0. So v of x1 is just equal to 5.75. It's just constant. I can sum moments, set them equal to 0, and I get m minus 80 minus 5.75 x1 equals 0, and I get m of x1 is 80 plus 5.75 x1. Okay, and again, you can see I can just take the derivative of this and get shear, but I can't take the integral. Well, I can take the integral, but you see I have to solve now and look at the initial condition that at x equals 0, I have a moment of 80 feet. So I'll show you what that looks like. Let's say I just wanted to solve for shear, and I want to take the integral of v of x dx, and I say, though, that's just the integral of 5.75 dx. I'm going to get 5.75 x1, but I have to add that plus c in. This is my moment function, right? Now I need to say, well, what is an initial condition I can use to solve for this? Well, I know that at x1 equals 0, my m is 80. And you can see here, if I plug this in, 5.75 times 0 plus c equals 80, I end up getting c is 80, and I get this function, m of x1 equals 5.75 x1 plus 80. Look how cool that is. Same function. Okay, so these are all the little checks you can do to make sure that you're summing your forces and your moments right, and that your statics is good, and you're doing everything correctly, okay? Okay, let's move on to cut number 2. So now I just have to cut somewhere in that distributed load. Okay, so I have the 80 kilonewton meter. I have the 5.75 kilonewtons here. I have the 15 here, and this is 5 meters from here to here. And then I have here some distributed load, and this is going to be my x2, right? Because 0 is, sorry, not 0. This would now be 5. X2 is between, not equal because the other one was equal, between x2 and 10. Okay, and of course, again, I've exposed some shear, some moment, and we have this resultant of 5x2. I think that's everything, okay? And then once again, we're going to come here and sum our forces in the y. Up is positive, negative v, plus 5.75, minus 15, minus 5x2 is 0. V is equal to negative 9.25 minus 5x2. And let's clean this up a bit. V of x2 equals negative 5x2 minus 9.25. And we have our function here for x2. So you can see this is a piecewise function. Okay, let's do sum of moments. Counterclockwise is positive. Okay, and I'm going to write this out now because I think you know how to do this, and you get negative 5 over 2x2 squared minus 9.25 x2 plus 108.75. Okay, after much work, we have all of the equations for shear and moment for our beam. That is the first part of this solution. And now we just have to draw our shear moment diagrams, okay? So again, I'm going to draw them here actually. A nice clean page. I'm going to draw our beam first, okay? And let's draw all the loading we have. So we have 80 kilonewton meters. We have 5.75 kilonewtons here. We have 15 kilonewtons. We have a distributed load of 5 kilonewtons per meter. And we know this reaction is 34.25, and that from here to here we have 5 meters, and from here to here we have 5 meters. Okay, that's all we need to draw our shear moment diagram actually. V is in kilonewtons, M is in kilonewton meter. Okay, we're going to do the same method, the graphical method for this. Okay, so let's put in all our important points here. So we need to make sure we consider this point. This is our end point here, and this is our beginning point. So we need to start here at 5.75, right? That's what's happening. That's the shear value at 0. Nothing changes, constant. And we can confirm that with our equation that we just derived. Okay, I get pushed down by 15, which puts me at negative 9.25. And then I have a distributed load, so I need to have a straight line going down. And by the end of this, I'll have negative 9.25 minus this resultant of 25, which puts me at negative 34.25. And then you see that that's where that reaction pushes me back up. Okay. Now, for my moment diagram, I get to start here at 80. Okay. I have constant shear, which means I just need to add that area. It's above the x-axis. I need to add 5.75 times 5. That's the area here. 28.75. So I go 80 plus 28.75 equals 108.75. That's the value I need to be at. And I know that it's just a straight line because it was constant before. Now I need to get back to 0. I need to take the area of these two sections and make sure that they're 0, and they are. And I'm going to have less of a negative slope, more of a negative slope, and just have to connect those. And that is it. Okay. So this is going to be the end of the first video, and I'm going to continue with the second part where we start bending deformation of a straight member. So this first part was really just the statics review, and then we're going to move on to the materials part where we connect basically internal moment and sigma, that stress value. All right, so stay tuned.